Hello, Pre-P Chemistry. How are we doing today? Hopefully, y'all are doing well. Mr. Oglesby here. So today we are going to be covering or continuing our notes on types of reactions. So today we're going to be starting with synthesis and decomposition reactions. Now, this is a two-part lesson. So today we're going to cover synthesis and decomp. Next class, we're going to cover single replacement, double replacement, and combustion. All right. So let's go ahead and dive on into this. So for a synthesis reaction, we know that elements are going to combine, okay? Anytime we talk about something being synthesized, what we're talking about is something that is being made, okay? When we talk about synthetic materials, those are materials that have been man-made, right? And so when we're talking about a synthesis reaction, we're talking about creating new substances from this one substance that we have, from two or more substances that we have. Now, these can be elements or compounds when we're creating with our reactants, but the products will always end up being one compound. Okay, so that's kind of a big defining characteristic, is that you're always only going to ever see for your product one product. Okay, so keep that in mind when you're looking at it. If it ever says that you created one product, then you immediately know that that is a synthesis reaction. All right. Now, if I were to actually look at this, so in terms of the particle view, looking at this, I start with substance A and substance B, and they combine to form substance C. And if you look, substance C is A and B mixed together. AB, 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 and so on. So that's what you will always see with a synthesis reaction. Essentially, we're going to see two or more elements or compounds, and it can be elements or compounds. I'll zoom out a little bit. Combine to form one compound. Okay, and so keep that in mind. Again, you're always going to have one compound. All right, I got this little picture here. We've got Princess Leia and Han Solo here. So 1 plus 2, A plus B produces a couple. All right, and so that would be a synthesis reaction. Now, there are 6 rules that you do need to follow when you're talking about a synthesis reaction. Okay, so I'm going to read through all of those because you do need to know these, because these are going to reflect what your product will actually be. Okay, so rule number 1, if I take two nonmetals, so looking on your periodic table, to the right side of that periodic table, the right side of that stair step, if I've got two things from there, all I'm going to do is form a common covalent compound. And what I mean by that is if I've got carbon and oxygen, then the common covalent compound would be CO2. Okay? Or if I've got nitrogen and fluorine, then we're going to make NF3. Okay? So what we're going to be looking for is a common covalent compound. Okay? Now, number 2 says if I take a metal and a nonmetal, we're going to produce an ionic compound. Okay, again, that makes sense, right? Metal, nonmetal, we get ionic. Okay, so metals are on the left side of that periodic table, nonmetals on the right. Again, ionic, which means we're going to need to remember to swap, drop, reduce. Rule number 3. Now, this is where things get kind of a little bit different, and it's going to be rules that you're going to have to keep in mind when we're solving for these things. So if I take a metal oxide, by metal oxide, I mean I've got like a sodium and an oxygen, so sodium oxide. Then what I'm going to do, if I add it to a nonmetal, if I add it to water, then I'm going to produce a metal hydroxide. Okay, so if I take a metal oxide and water, I'm going to produce a metal hydroxide. Rule number 4. If I take a metal oxide, again, metal oxide, but this time I add it to carbon dioxide, I'm going to produce a metal carbonate. Okay, so metal carbonate. Remember, carbonate is CO3 with a -2 charge. And hydroxide here for that first one is OH with a -1 charge. Next, if I take a metal chloride, so any metal plus chlorine, so sodium chloride, magnesium chloride, rubidium chloride, anything like that, and oxygen, I will produce a metal chlorate. Okay, so chlorate is ClO3 with a -1 charge. And then the last rule says if I take a non-metal oxide and water, I'm going to produce an acid. Now, to produce an acid, basically, you're just going to add the two together with the hydrogen being in the front. Okay? All right. So let's take a look at this. So question number 1 says, write a balanced equation for the reaction that will take place when potassium reacts with chlorine gas. So I have potassium, and it reacts with, so plus, chlorine gas. Now, chlorine gas, remember, chlorine is a diatomic element, so it would need to be Cl2. Okay? Now, what are we going to produce? Well, looking at this, potassium is a metal, chlorine is a nonmetal. So what do? Well, that's rule number 2 here. So metal and nonmetal produce an ionic compound. So I would produce potassium chloride. Okay, KCl. Now, I would need to remember that since it's ionic, I do have to swap, drop, reduce. I have to cancel out those charges. Potassium has a +1 charge. Chlorine has a -1 charge. Those charges are going to cancel out, so we just need 1 potassium and 1 chlorine. The very last thing would be to go back in and balance your equation. So I have 2 here and 2 here, and then that would be my balanced equation. Okay? All right, so let's take a look at the next one. So it says, write a balanced equation for the reaction that will take place when aluminum is allowed to react with oxygen gas. So I want y'all to go ahead and try this on your own. So pause your video, work through this problem, make sure to balance it, and then we will go over it after you have finished. So don't forget to resume your video afterwards. All right, so pause your video. All right, so this is what you should have ended up with. So I ended up with 4 aluminum plus 3 oxygen produces 2 aluminum oxide. So I did end up going in and balancing. It took 4, a 3, and a 2 to get all of that to balance out. All right. Now, this was essentially the same as question number 1, right? We took a metal and we took a nonmetal and we produced an ionic compound. All right, so the next one here, it says if iron 3 nitride is the only product formed in this reaction, write a balanced equation for the reaction. So what this tells me, it says that it is the only product. So since there's only one product, I immediately know that this is a synthesis reaction. So I have FeN as my product. Now, how do I know it's FeN? Well, iron, they told me, had a +3 charge. Nitrogen has a -3 charge. Those charges are going to cancel out, so I can go ahead and get rid of them. So what did I start with, though? Well, I started with an iron and nitrogen, right? So I have nitrogen. Remember, nitrogen is a diatomic, and iron. We would need to go in and balance, so we'll put a 2 right there and a 2 right there, and then that would be balanced. So essentially we just took this and we worked backwards, right? We knew that we ended with that common ionic compound, and so we knew that we started with the pure metal and the pure nonmetal. Okay? All right. So now I want y'all to go ahead and give number 4 a try. All right, so give number 4 a try. So pause your video, work through number 4, and then we will go over it. All right, so y'all should have ended up with 2Ca plus O2 produces 2CaO. And so looking at that, I then can see that I've got calcium plus oxygen, metal plus nonmetal produces a common ionic compound there. And so then I would need to go back in and balance it. Number 5 is a little bit different here. Number 5, we have SO3 plus H2O. Okay, so in this case, I've got a nonmetal oxide. Okay, a nonmetal oxide and water. So this is nonmetal oxide and water. So looking back at my rules, rule number 6 says if I've got a nonmetal oxide and water, they're going to produce an acid. So to produce an acid, all we need to do is add everything up with hydrogen being in the beginning. So I have hydrogen, there were 2 of them. I have sulfur, there's only 1 of those. And then I have oxygen, there are 4 of those. So then this would be my final formula, with my product being this H2SO4. Okay? All right. So I'm going to leave that last one as practice for y'all. But again, you do need to make sure that you've got those rules memorized, because those rules are basically just going to tell us how to solve each of these problems, how to put everything together. Okay?
All right, y'all, so next one we are going to do is a synthesis reaction. It's going to be between aluminum and iodine. All right, so I'm actually going to start with some aluminum powder. Now, aluminum powder is actually very, very flammable, and so I'm going to be very careful with it because I don't want it to catch on fire. And then I'm going to take some of this iodine, and this is just solid iodine, and put it into the center of that. What I'm going to do is I'm going to add just a little bit of water. So that's what it's inside of this pipette. I'm going to add a little bit of water to that, and we're going to see what happens.
All right. So now let's take a look at decomposition. So decomposition is basically synthesis, but opposite. So instead of building up, we are breaking down. All right. And so remember that decomposition, you're basically going to do the exact opposite of what you did with a synthesis reaction. Now, a big defining characteristic of a synthesis reaction was you had one product, right? Well, a defining characteristic of decomposition is you have one reactant, okay? So we're going to start with one compound, all right? So we do need to keep that in mind. We need to keep looking for that. Again, it's an easy way for us to identify if it's decomposition or synthesis just by looking and seeing how many reactants, how many products. If there's only one reactant, I know it's decomposition. If there's only one product, I know it is synthesis. Okay. Now, in a decomposition reaction, it's basically going to break down into its smaller parts. Now, it could break down into 2 or more compounds. It could also break down into 2 or more elements. And so keep that in mind when you're looking at these decomposition reactions. They are going to be breaking apart into pieces. Now, these do have rules as well, just like your synthesis reactions. And so you will need to make sure your rules are known. You need to keep those in mind when you're solving these decomposition reactions, okay? All right. So there are 6 rules for predicting the products of decomposition reactions. And these rules are basically the same as what you would see with your synthesis, but opposite, right? We know that our synthesis reactions were building up. So with decomposition, since we're breaking down, then they would follow the rules in reverse. So let's go over those. I'm actually going to go over each one of these because each one of these covers a different rule So we'll kind of see what they look like. Okay. Now, one thing to note is that for decomposition, you do tend to need some form of energy for that to occur. And that could be energy from the air. It could be adding energy through a heat source. It could be adding energy through something like electricity. And so we will kind of keep that in mind when we're looking at a decomposition reaction. But it ultimately shouldn't be something that y'all are going to be needing in terms of trying to figure out how to solve a problem. Okay. So here we go. Starting off, for this first decomposition, the first rule says that binary compounds form the two elements that make them up. Now, first off, what is binary? Remember, binary means you have two elements. So these are going to be compounds that have only two elements present. And this basically is rules 1 and 2 in your synthesis reactions. Okay, so if I take two elements here, what they're going to do is they're going to break apart into their base parts, just into the elements that make them up. And so here I've got mercury and oxygen. Now I put O2 there because oxygen is a diatomic element, so you do need to remember that oxygen will be found in O2. Okay, then I would go in and balance, which would be A2 and A2. Y'all, I have done this a lot, so balancing equations is a lot of times fairly simple for me. I do want y'all to probably get in the habit of just kind of solving it like we did in the notes last class. Okay? All right, moving on. So next would be rule number 2, which says metal carbonates produce metal oxides and carbon dioxide. So remember, a carbonate is CO3. It's got a -2 charge. And they're going to produce metal oxides and carbon dioxide. So this metal oxide would be metal with an oxygen of some variety. Okay. Now this is actually going to be rule number 4, but in reverse for your synthesis. And so what I see is this is going to break apart into the metal oxide. So my metal here is calcium oxide, O. Calcium has a +2 charge. Oxygen has a -2 charge. So those charges do cancel out. And carbon dioxide. Now I would need to make sure I go back in and balance this equation. I've got 1 calcium on the left, 1 on the right. I've got 1 carbon on the left, 1 on the right. I've got 3 oxygen on the left, and then I've got 3 on the right as well. So that is already balanced for me. Next, I have metal hydroxides. They are going to produce metal oxides and water. And this is basically rule number 3 for your synthesis rules, but again, in reverse. So here, what I'm going to do is this is going to produce, again, a metal oxide. So my metal is calcium. It's going to be with the oxide there. And water. And so looking at this, that is, again, already balanced for me. So I don't need to go back in and add any coefficients to that to balance it out. Next, if I've got a metal chlorate, that is going to produce a metal chloride and oxygen. Now that's going to be rule number 5, synthesis, again in reverse. So this breaks apart into a metal chloride, sorry, not M. Metal would be K, potassium here. So I've got K and chloride, so KCl. Potassium has a +1 charge. Chlorine has a -1 charge. And oxygen. Now looking at this, this does not go ahead and balance out, so we would need to go back in and balance this. It's going to require a 2 right here, a 2 right here, and a 3 over here. All right. Next, acids with oxygen in them produce water and whatever is left. And so this is basically rule number 6 here. So here I've got an acid. How do I know it's acid? Well, it starts with hydrogen. So it's going to produce water, H2O, and whatever's left. So if I've got 2 hydrogen already and 3 oxygen, well, there's only 1 oxygen over here. So I'm producing CO2. Okay, so when I'm looking at that, I can recognize that just based off of everything adding up, we do need to make sure that everything cancels out. If you do feel like you need to add coefficients, then you should just go ahead and change your compounds to make sure they add up to whatever is left at the end of that. Okay? All right, next one. Now this one is a word problem. So here it says crystalline bismuth oxide decomposes with heat. So we've got bismuth oxide, it is decomposing. I want y'all to go ahead and solve this problem. So pause your video, solve this problem, and then we'll go over it. All right, so you should have ended up with 2Bi2O3, because that would be that bismuth oxide there, right? We had a bismuth with the charge of +3, oxygen with the charge of -2. Got to cancel that out, so swap, drop, reduce. And that's going to decompose with heat, okay? And you actually could show that with heat, right? Remember on the last set of notes, we talked about how if we add heat, what we would do is we would do a change in heat over the top of that arrow there. And then +4 bismuth and 3 O2, okay? All right, I'm going to leave these last two as practice for y'all to do on your own.
All right, y'all, so now we're going to do a demo with a decomposition reaction. So what we've got here is we've got some hydrogen peroxide. I'm going to add some food coloring in that. That's just to make it pretty, make it a little easier for y'all to see. We've also got this right here. Now this is actually potassium iodide, and it's going to act as a catalyst for this reaction. Now remember, what does a catalyst do? A catalyst only speeds up a reaction, right? Okay. Inside of that, I've actually put a little bit of dish soap. That just makes this all the better, okay? It just makes it look way, way, way cooler. Okay, so I'm going to start. I'm going to add a little bit of food coloring into the bottom of this. So I'm trying to mix in some of that food coloring into that hydrogen peroxide. See if we can get some of that color coming out of it. And then I'm going to add about 50-ish milliliters of hydrogen peroxide here. Okay. And I am going to go ahead and put that in here.
Ooh.
All right, so that bright blue, well, actually dark blue color there. And now what I'm going to do is I'm just going to quickly add this potassium iodide, this catalyst, to the hydrogen peroxide, and we will see what happens. Now, what do we see? Hopefully y'all can see it right here. Coming off the top of it, there's actually steam. And so that's telling us that it's releasing that energy, right? So it's exothermic. Okay? All right, there you go. Now, what do we see? Hopefully y'all can see it right here. Coming off the top of it, there's actually steam.
Alright guys, so this is our next demo for decomposition. And in this demo, we're going to look at the decomposition of potassium chlorate. So potassium chlorate actually comes into one of these containers because it is a fairly reactive chemical. It's a strong oxidizer. And so it actually comes in here, it's just a fine white powder. I've already added it into my test tube and I'm heating it up to melt it. Alright, and once it's all melted, I'm going to add a gummy bear. So here's my gummy bear that I'm going to add. You can name him whatever you want to. I feel like most often the gummy bears get named Fred. Just in my class, I don't know. All right, and so I'm gonna add him in there and we're gonna see what happens. Now, gummy bears are primarily made up of sugar. And the gummy bear is not gonna be used up in this reaction, but it is going to act as a catalyst. All right, we'll see what happens.
But otherwise, that is it for the lesson for today. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.